All right, so the first question is, what is chemical engineering? Now, we had a head of school and professor for a long time, Rolf Prince, who passed away a couple of years ago. And he used to make the point that chemical engineers don't make chemicals, they make money, um, which is a bit of a simplification, but it gets across a point that we make chemicals and we do other things, and we have to do it in a way that's profitable. In fact, there's more constraints than that. We have to do it in a way that's safe and hopefully in a way that's sustainable. Okay, so what is chemical engineering? Well, it's a multidisciplinary branch of engineering. There's definitely a fair bit of chemistry involved, but there's also quite a bit of physics, biology, mathematics, microbiology, economics, mechanical design, and so on. Chemical engineers design, develop, they produce, transform, transport, they operate, and they manage lots of different industrial processes that turn raw materials into useful and valuable products. So chemical engineers need to understand the chemical basis of the feedstocks and like they're dealing with, to develop designs, to manufacture, to operate, and to develop new substances and new processes. Okay, and we have to consider economic viability, back to Rolf's point, management of resources, health and safety, sustainability, and environmental impact. Okay, so it's not just chemistry, it's not just trying to make money, it's trying to do that in a safe and sustainable way. A good way to understand where chemical engineers or what chemical engineers do is to think about where do they go. So more than half of our graduates go into engineering type jobs. Okay. And some of the companies are listed here. So everyone who had anyone who had toast this morning or bread on their sandwich for their lunch, it's quite likely that the yeast used to make that was made by this company, AB Mauri, who employ quite a few of our graduates. For people who like to give themselves a bit of a treat with some Lindt chocolates, one of my former students is their production manager. We all would have made use of Sydney Water's products today, and companies like Stantec, Oricon, WSP, and Sewers are involved in things like design for Sydney Water, both water supply and wastewater treatment. Many of you will have products in your homes from companies like Unilever and Johnson & Johnson, and again, quite a few of our graduates go there. We still have quite a few graduates going to the more traditional chemical engineering industries like BOC gases. So if you ever see a hospital, you see the oxygen tank there supplied by BOC. If you know anyone who's in sort of welding and fabrication, all those gases are from BOC. We have students still who go into the oil industry, particularly a lot of our international students. So in our school, we have quite a few international students from Malaysia. A lot of them are sponsored by Petronas, which is their big oil company, and the owner of those two big towers in Kuala Lumpur. We have students who go to work for Shell and Rio Tinto. So we have students who go to a whole big range of areas. About a quarter of our students go into finance and consulting kind of roles with banks and insurers and consultants. And interestingly, companies like EY are now actually getting into engineering design as well. So they've been employing engineers to do consulting work. Now they're starting to employ engineers to do engineering work. About 10% of our students go on to further study. Most of those are research for PhDs and masters, and a few of them go to medicine and law and those kind of degrees, but mostly it's research degrees. Okay. Now, at the moment, it would be a very exciting time for us because we should be in our new labs doing our teaching at the moment, but we're all working from home at the moment. But for you young students who are thinking about joining us, we will be teaching in the downstairs lab of that building from semester 1 next year, and the upper floors will be fitted out for research. So if you come and join us, you'd be doing your research thesis there with us. We got any questions so far? Not yet. Okay, but any questions, feel free to put them in the chat, and I'm going to stop fairly regularly to have a look. Okay, and this is a picture of our downstairs lab. This was during the break, and so final little bits of fit out were being taken or being undertaken, and it would have been ready basically this week were it not for the coronavirus disruptions. But we will get that fitted out over the summer break, and we'll be ready for first year and second year and third year teaching in there from semester 1 next year. Okay, this is what our chemical and biomolecular engineering degree program looks like. So just an overall idea of the degree. So in the first year, you study mathematics and chemistry, computing, and 3 chemical engineering subjects. One that introduces chemical engineering, another that studies mass and energy balances, and a third that essentially looks at mass and energy balances, but from the perspective of sustainability. In your second year, you study how fluids move, so how liquids and gases move around plants. We do more applied maths for chemical engineers because a lot of our designs really involve calculus for working out how big a reactor is, and things like that, or they involve statistics for working out how to do good experiments, okay? And heat and mass transfer, so how do we use energy? How do we get gases into solutions? How do we extract things from solutions and so on? The second semester, we look at thermodynamics, really about how energy is used, okay, and how compressible gases flow. We look at different separation technologies, particularly membranes and other separations like distillation and air stripping and so on. And then we have a multidisciplinary project that you undertake with other potentially with other engineers around the faculty. And if you're doing the standard engineering degree, you do some more chemistry here. In third year, then we learn how to design reactors, how to control chemical plants, how particles move around chemical plants. So not everything's a gas or a liquid. There's quite a few solid-based processes. And we have another interdisciplinary project with other engineers. We look at how do we design overall plants. The one in red here is one of the subjects I teach, Biochemical Engineering, where we look at how do we use microbes and enzymes to do useful things for us. And we study safety and economics. In our final year, we take 2 design projects, we do a thesis, which is a big research project, and we've got 4 electives plus 1 here in the third year where you can specialise in an area. Okay, now in the subjects I cover, Biochem Eng and Design A, I'll talk a little bit about those to give you an idea what the kind of things you'd learn in your degree. Okay, for our specialisations, you can specialise in the areas of food and bioprocessing. You can specialise in the sort of use of data in industry, in Industry 4.0. In process intensification, which is a set of words about making things smaller, more environmentally friendly, more efficient, or in water and environmental treatment. Okay, one of the things we're very proud of in our school is we have a program where about a quarter of our final year students go and undertake their thesis in industry. So if we go back to this, we go back, rather than being with us for that first semester, we give them credit for this design subject, both their thesis subjects and 1 elective. So they're away for this whole first semester. And they undertake a big project in industry or with a community organisation, and they're paid a scholarship to do this. So they could be at, say, AB Mauri, the baker cheese company, where Henry was here. They could be with a regional council somewhere in New South Wales looking at the water supply, or they could be, in this case, with Dow overseas, as Isaac was here. Okay, so we've sent people all over New South Wales still this semester. We haven't sent them overseas for the past 2 years, fortunately, but we will be able to do that again soon. Now, about 40% of our students take a combined degree that are typically 5 or 6 years. There's a bit of variation there, and there's some updates there. So some of them will be 5.5 years in future. And the options are people take a combined degree with engineering and a Bachelor of Arts. Now, that's not necessarily fine art. It could be languages, music, philosophy, psychology, and so on. I had a student a few years ago for his final year thesis with me, and he'd done his combined degree with arts. He majored in psychology. Now, he didn't go off to be a psychologist. He went off to work in the pharmaceutical industry because they were really interested in someone with a background in psychology for helping essentially with safety, to understand the human side of safety, not just the scientific side of it. We have a lot of students undertake combined degrees with commerce, and finance and marketing and business information systems are pretty popular. And a lot of those will go off to work for some of those in that area between engineering and commerce in those consulting companies, but some will go to engineering. We have 1 or 2 students every year who are combined with law. Okay, and then we have our biggest cohort of combined degree student, second biggest, well, probably equal biggest with commerce, is in combined with science. And here's some of the majors that people commonly pick, but there's a lot of other majors you can pick in a science degree. Any questions so far? Ah, good. We've got a few questions. ATAR cutoff. Okay, all right, let's go from the questions here. So, maths course in high school, would I recommend? Extension 1, we'll get to that on the next slide. You guys are great at anticipating. Prerequisites is next slide. So I might just go ahead 2 slides and then I'll come back to the question. So, okay. Okay, so recommended units of study and prerequisites. So these are a couple of the questions. So what we would recommend for chemical engineering is that you study mathematics extension 1 or higher if you want to, but extension 1 is the recommendation, as the minimum. Chemistry, again, is very strongly recommended. We'd also really encourage you to study another science, but we understand in programs there's a limit to how many you can fit, but also that all of these sciences, whether it's physics, biology, anything in the computing information space, or any engineering studies, if those subjects are still available, they're all equally valuable to you in the rest of your degree. So the 2 we'd emphasize would be to take mathematics extension 1 and to take chemistry. Now, engineering as a whole has prerequisites. So the minimum is for you to have studied mathematics advanced and to have achieved a band 4, or mathematics extension 1 and to have achieved a band E3, okay? And these were chosen based on essentially your probability of passing first year maths and then not delaying the rest of your degree, okay? Now there's some detail here at these web links for the prerequisites, okay? And there's also some alternative pathways. But if you're still at the point where you can make a decision, please look at mathematics extension 1 and chemistry. Okay, if you're still at that point, if you're in year 10 and about to decide your subjects, and if you're in year 11 and you're thinking of studying engineering, please stay in mathematics extension 1. There was some odd advice around a couple of years ago recommending students drop down to get a better ATAR. It turned out not to be true, and it really disadvantaged quite a few students. Okay, so recommended for all engineering to do mathematics extension 1. The minimum is mathematics advanced. We'd also, in chemical engineering, really strongly encourage you to study chemistry and another science, but that other science could be any of the other sciences offered in the HSC. Okay, let's have a quick look at the chat. Okay, so, all right, ATAR cutoff. Sydney University operates on a system of guaranteed ATARs. Okay, so at the moment, the guaranteed ATAR is 92 for chemical engineering. Now, there are some alternative entry pathways, but we also don't really know how the whole HSC is going to play out. But there will be, I guess, approaches made by UAC and the Department of Education, Board of Studies, and so on for how we're going to manage the HSC, depending on coronavirus numbers and so on. Okay. How much of the learning is practical? I think we have, okay, so in your chemistry subjects, you're typically doing a lab every week or 2 in those 2 subjects. In the chemical engineering subjects, when we counted it up for our accreditation visit 2 years ago, which was the last time that things were normal, I think there are about 13 or 14 different experiments that were done through the degree. The students also undertake about 3 months worth of work experience. So there's a fair bit of practical learning, and there will be more because we have a new building with a big lab and we have a good budget for fitting that out. Okay, do we study a lot in composites, for example, carbon fiber? Personally, myself, no, but there is a big research section of our school who work on carbon nanotubes, carbon fiber, graphite, and so on. So there's a lot of people who study composites, but just not myself personally, okay? If you're interested in that area, there's a lot of opportunities in final year thesis in that kind of area. For scholarships for the program, I know if I count backwards from 4th year a quarter of our students get that MIP scholarship, and that's about $19,000. So that's quite good for their final year. There are other entry scholarships. There's one named after Rolf Prince. There's other sort of general engineering scholarships. I think we have one called the Loxton Scholarship, which because of its conditions is only for male students, but there's many female students get other scholarships. Okay. Guaranteed ATAR to get into the course. I'll check that one, Isabella, and get back to you. Okay. I think there are some adjustment factors, but they're not very large. Okay. Okay. Would it be possible to take this without having taken chemistry in high school? Yes. If you look at this link for bridging courses, there are chemistry bridging courses. It may, there is a slightly different first year chemistry pathway where you take a lower level first year chemistry, and then you may need to do a second bridging course before second year. But yes, it is possible. Okay, we do have a few students doing that. It's not recommended, but we have had a few and they've done quite well. Okay, so yes, it is possible. The prerequisites are the strict rules. The recommendations here are our strong guidance. Okay, good. They're a good set of questions. So. Okay, so what do the students do? So I'll give you some examples in my unit. So in 2019, we ran a laboratory where the whole class worked on this, where we were growing a kind of fungi called Rhodotorula that's got a lovely pink color. And we were looking to try and make more of the pink color or make a nice red color. And the reason there is there's a lack of pink to red food colorings that are both natural and heat stable. And these things are actually quite in demand when you look at the sort of fake meat market with all those sort of new vegetable-based burgers. They want them to have that sort of pinkish color inside. Okay. And so the whole class was involved in, we'd get these Rhodotorula fungi, we'd grow them, we'd expose them to UV light, we'd then plate them out, we'd look for mutants with a good color, we'd then grow them again. And then we'd measure the pigment profile and see what we could find that was better. And they had many paper-based projects for looking at running a factory that makes yogurt starter cultures, looking at biofuel production, looking at monoclonal antibody production. So we try and give you a lot of breadth in the topics we look at. Now in 2020, because of COVID, everything had to be sort of paper and computer-based. And so the students looked at designing a penicillin production plant and a vaccine production plant. The other subject I take is called Chemical Engineering Design A. So the last 4 or 5 years, we've actually been looking at some quite open-ended design processes. So 2017, 2018, we were looking at how do you remediate PFAS? Okay, it's probably a chemical most of you have seen in the news. If any of you live around Newcastle, it's been big news there because of runoff from the Williamtown RAF base or Newcastle Airport. If there's anyone dialing in from Toowoomba, it's been huge news there because of Oakey and so on. And so the students, over those 2 years, we had students look at probably close to about 100 different treatment options for how you treat this PFAS that's getting into the ground and then moving in the groundwater. In 2019, we asked the students to look at how do you produce battery-grade lithium for export. Most people aren't aware that Australia is currently the world's largest lithium exporter. Okay, it's a hard rock ore several hard rock ores are mined in Western Australia. They're then crushed and roasted and dissolved and precipitated and then shipped off to East Asia to make the batteries that are powering all the devices that we're probably watching this presentation on. Okay, so asking the students how to make battery-grade lithium. 2020, we had a look at hydrogen for export. And again, Australia is one of the world's largest exporters of liquefied natural gas, LNG. And Japan is now one of our biggest customers, and they would much prefer to buy hydrogen. So we looked through what are the options for hydrogen for export. And this year we decided to turn it around and look at import replacement. So Australians are, quite frankly, as a nation, addicted to coffee, but we produce about 1% of our consumption and export half of that, mainly to Japan. And realistically, we're only producing about 0.5% of our coffee consumption. Okay, and there's a fair bit of room for growth there. Okay, and this is a subject here where we make use of a lot of industry input. So 2017, 2018, I scoped out some of that project with a former student who now is the general manager of a company called ICD Asia Pacific, and we're actually doing research with those folks on breaking down PFAS since then. 2020, we had hydrogen experts from BOC come in via Zoom. This semester, 2021, we actually had four global coffee experts who'd worked with companies like Nestle and JDE and GEA, the biggest equipment supplier in the coffee industry. We had someone give a guest lecture from Denmark. Okay, so all of this having to be on Zoom, we found a way to turn some of it into a positive. Okay, and so we make a lot of use of industry input into our. Okay, so my story. Now, I was thinking how I'd draw this up, and I was going to draw it fancy chemical engineering style with the recycle, but I came from a high school in country New South Wales, so I put a logo in there. Studied chemical engineering at Sydney, both BE and PhD, and this was what our logo looked like in those days. It was a little bit fancier, not quite as computer friendly. I then joined Kodak Australasia. Now, does anyone on the call, particularly the high school students, know what Kodak did? Yeah, films. Okay, yep, film. Yep, like photographic film. You've actually got the answer exactly right. They still do a few other things, but what they made their money in was the photographic films. Okay, they also did photo processing. They made cameras. They made paper, but all the money was in film. And as the world went to digital, and then computers were able to handle the images. Okay, so there was a time when to get a decent quality photo, you really need a 1 to 2 megabyte file. And there was a time that you folks won't remember because it was before you were born, where a 1 to 2 megabyte file was actually quite big and hard to handle. Once a 1 to 2 megabyte file became easy to handle, they basically went out of business, okay, because all the money was in the film side of it. Interesting though, they had a product called Kodak Easy Share, which was a website that you could share your photographs on with your friends. And this was made in 2003. And I think that was a few years before Facebook, but it just didn't quite take off the same way. Okay. But I came back to Sydney Uni in 2005 to teach chemical engineering. Okay. The areas that myself and my students do research in, we do a lot of research in things called bubble columns. We've done a lot of work on fermented food and algae, particularly around vitamin K, and we've done other work on membranes and biorefineries. I'm going to just chat a little bit about these two areas. So for bubble columns, we built a 1/1000th scale bubble column. So the real ones are at big baker cheese factories. This is one in our building. It's 1 to 200 litres. The real ones are 100,000 to 200,000 litres, okay? The full-scale bubble column has 400 million bubbles in it. You can't possibly track them all or give them all names, so you have to make all kinds of assumptions. Here's a picture of the big ones looking up at them. This is actually 12 metres tall. I think we're already at least one floor up off the ground to take that photo. And we're interested in sort of what the volume fraction of these bubbles are, how well it mixes, how well we get oxygen in. We can then make models where we look at if we drop the sugar into the top of the fermenter, how does the sugar mix around? Do we get really big high concentration zones? Do we have zones where the cells are starving? And then we can actually start designing better bioreactors. Okay, we can even go a step further and say, let's have an imaginary yeast particle and let's look at how it moves through the reactor. And so we can actually compare different designs in a computer without having to build very expensive bits of equipment then to see which one might give a better result. Okay, we've done a lot of work on vitamin K2. Now, the hope in some of the research is that vitamin K2 can help keep calcium in your bones and out of your arteries. Okay, keep in mind, I'm not a medical doctor, so I'm not necessarily recommending you all go and take this. Okay, and what we were trying to do was we were trying to produce large amounts of vitamin K2. Now, if there's anyone who eats a lot of Japanese food on the call, some of you may have tried natto. Has anyone tried natto? Sound of interest? Anyone tried natto? Or some of these other ones? Well, I think the polite thing to say is they're an acquired taste. the Bacillus subtilis bacteria that grows on these makes the vitamin K2. It makes this stringy biofilm, which is a texturally, it's what people like about the food. It also makes some fairly bitter tasting antibiotic molecules called bacitracin and similar, but quite small amounts. And it's an acquired taste, I guess, in a similar way to Vegemite being an acquired taste. So we came up with a method of growing the bacteria in a stir tank fermenter. We added oil both to stop it foaming and to extract the vitamin K. And we came up with a way of essentially the papers advocating for vitamin K recommend about 0.2 of a gram per day, so 200 milligrams per day. And if we they got a daily dose for health benefit of a couple of 100 milligrams, now, if we were to try and obtain that by eating cheese, we'd be looking at a physically impossible of 3 to 8 kilograms of cheese per day. Okay, it would not do your health any good to eat that much cheese. If you're eating natto, it's 1 or 2 serves a day will get you there, 16 to 20 grams. It's about 1 serve. The oil we were producing from our bioreactor from growing that same bacteria just under different conditions, you needed 0.2 grams per day, which is a fraction of a mil per day. Okay, and you may see this appearing in a breakfast food at some point in the next little while. Okay. Now, to give you an idea what some of our graduates do, now I've picked people who are a little bit older so you can see sort of down the track where people might be. So this is one of my classmates, Arthur. He's a consultant at Recce Pharmaceuticals, also works with AB Mauri, and he's worked on scaling up the production of a new type of drug to target superbugs, okay, using his chemical engineering knowledge. Naseem did a PhD with us, and she's now an assistant professor in tissue engineering at UCLA. Okay, Chris Jansen did a combined degree with us, I think combined engineering and commerce, but stayed in engineering. And he developed a robotic method to get catalysts out of reactors, okay? In chemistry, you folks will write equations and you just write the word catalyst on top of an arrow. In a chemical engineering sense, a catalyst is generally a sort of spherical particle with little bits of, say, platinum metal all over it. They tend to be quite reactive, and when they're exposed to air, they get hot. And when people are sent in to clean out the catalytic reactors, they can often have problems like their boots melting. There's a lot of safety problems. So Chris has won several awards for this robotic catalyst removal system. Okay, Ali Fardi did one of our postgrad degrees with us, and he's founded a company. I think they've got a new name now. They were called Triumph. If you Google Triumph, you'll still find him. I've forgotten his new name for his company. Okay, but what he came up with was a biomaterial that was liquid at room temperature, but solidified at 35 degrees or 37 degrees. So you could inject it into things like cartilage so your knees can repair themselves. Okay, and Aaron was a classmate of mine during his PhD. He'd studied in the US and came to us, and he heads up a company looking at making T cells for various treatments. Okay, so that's a sort of quick overview of chemical engineering. I'm just hoping to see questions now.
Okay, looks like there's no more questions. Thank you, John.
Oh, right, there's a couple of others that have popped up here. Hang on.
Oh, yeah.
Yes. About exchange. So, okay. All right. So the University of Sydney had a really ambitious goal to send half of our students on exchange during their degree program. Exchange for the moment is not happening this year. There's talk of it next year. I think realistically it's probably 2024, because at the moment airfares are incredibly expensive. You need government approval to leave the country and so on. So, but if you folks are in year 12, first year would be 2022, second year 2023, third year would be 2024, and that's actually when most of our students go on exchange. And we have quite good agreements and programs set up with places like Imperial College London, INP Toulouse in the south of France. It helps if you speak some French if you want to go there. KTH Stockholm, who teach in English. We had quite a few students go to European universities where they taught at least some of the subjects in English. We've had students go to Chinese universities for winter schools or summer schools. So there were a lot of opportunities being set up. We're very keen for it to happen, but realistically, it's probably when you're in third year is when that's likely to occur. So it's a good question. It will come back. Okay. There's just one other question I'll answer quickly. Projects we can undertake in high school. We do, in our school, we have run a very active sort of work experience program 3 or 4 times a year where you can come and visit and do some sort of hands-on stuff in the lab for the day. I'd be interested to see what's in the HSC chemistry curriculum. There's probably some things there where our school could put out some material and so on that might be useful to everyone. Okay, well, it was nice talking to you all. Hopefully I'll get to see some of you in person in the next couple of years. And hopefully these sessions are useful to you working out what you want to do, okay?